Motion. Skiers, sailors, hockey players, race car drivers, what do they all have in common? For all of them, understanding motion is crucial. There are two ways that motion is measured. We can have scalar quantities or vector quantities. And the basic meaning of that is with a scalar quantity, we're really only measuring the magnitude or size of something. So it would be giving you a number, but it wouldn't really be giving you a direction. For example, you could say, I live 1 kilometer away from the school, but what does that mean exactly? It doesn't really give you enough information. For example, do you live 1 kilometer north of the school? Do you live 1 kilometer west of the school? In which direction? We don't know because with a scalar quantity, we only know the actual quantity, but we don't know anything about direction. With a vector quantity, we get both magnitude and direction. It describes the size of a measurement, gives us a number, and also the direction. So for example, you might say, I live 1 kilometer east of the school. That gives you a better idea of exactly where you live. Similarly, if we look at the magnitude of a vehicle, we could say, okay, the car is traveling at 60 kilometers an hour, but it doesn't really give us any direction of where it's traveling, what direction it's traveling. A vector quantity would tell us not only the speed it's traveling at, but also the direction it would be traveling at. And you could probably appreciate that if you were a police officer, you were following a car, pursuing a car, and you wanted to let other vehicles or other police officers know where the car was, it would make a lot more sense to use a vector quantity than it would make to use a scalar quantity. Let's look at some terms we'll use while talking about vectors. The first one is distance, and you're probably familiar with distance. Distance is a scalar quantity. It describes the length of a path between 2 points. For example, 10 meters. You could say the fire hydrant is 10 meters away from the tree. The odometer on your car measures how far you've traveled from your house to, let's say, your soccer game. It would let you know that you've traveled a total of 10 kilometers. It doesn't tell you what direction though, and that's why distance is a scalar quantity. Position, on the other hand, is a vector quantity. It's very similar to distance, but in addition to telling us the distance of something, it also tells us the direction or where exactly it is in reference to some other point. So to show that, we use the symbol D with an arrow over top of it. In this way, we know that it's a vector quantity. So if your home is the reference point, you are 10 kilometers from home when you arrive at the soccer game. If we still use home as the reference point, you are 0. We say we're 0 kilometers from home after the soccer game. What it really means is that if we use home as a reference point, we're right back where we started. Time is another thing we're going to measure. It's a scalar quantity. It describes when an event occurs. It's measured in seconds. You could say, I left home for school this morning at 8:15. That would be your starting time or your initial time. And we symbolize that with a T and a subscript I. The I stands for initial. If you arrived at school at 8:30, that would be TF, or the final time. It's when the event ends, your walk to school. To show how long it took to get to school, you would use the formula delta T, or change in time, equals TF, or your final or arrival time, minus TI, your initial time. So that would be 8:30 minus 8:15, because 8:30 is the final or arrival time, and TI is the initial or starting time. That comes out to 15 minutes. If we wanted to plug this number into another formula, we would have to convert 15 minutes to seconds. That would be 15 times 60 seconds per minute, and that would give us 900 seconds. Displacement. Displacement is another quantity we might want to measure. Don't forget that the symbol for displacement is a D with an arrow over it because it's a vector quantity. It includes not just how far, but also which direction. Describes the straight line distance and direction from one point to another, how much an object's position has changed. If an object ends up back where it started, its displacement is 0. Let's take a look at an example. We'll use our point of reference as this fire hydrant. Let's say you're traveling west toward the fire hydrant and you're at 9 meters east away from it. On the other side of the fire hydrant, there's a tree that's 5 meters away from the. So your final position is 5 meters west of the fire hydrant, and your starting position or your initial position was 9 meters east of the fire hydrant. That's still not very useful. When we use vectors that are opposite in direction, for example, east and west, it's convenient to designate these directions as either positive or negative. It's common to call east positive and to call west negative. Thus, 9 meters east becomes positive 9 meters. And 5 meters west becomes negative 5 meters. That tells us that the total displacement is minus 14 meters. In other words, you are 14 meters west of your initial position. So we'll always say that west is negative and east is positive, but we can also do the same thing for left. Left is negative and right is positive. Sometimes we're talking about north and south, so we'll always call north positive and south negative. Similarly, we'll say that up is positive and down is negative. So that's not unlike a grid that has 4 quadrants. And if we wanted to think of this as north, south, west, and east, we can see why north is considered to be positive and south is considered to be negative, west is considered to be negative, and east is considered to be positive. Similarly, we can see why up would be considered positive, down would be considered negative, left is going to be negative, and right is going to be positive. So just keep those in mind. Objects travel with equal displacements in equal time intervals. We might think of this as an object traveling at a constant velocity, like a car traveling at 60 kilometers an hour over a period of time. If an object like this ball is rolling at the same velocity, or if it's traveling at a constant speed, that means it's going to cover the same amount of distance, let's say 1 meter, in the same time interval. So it takes, let's say, 1 second to cover 1 meter here. It should take 1 second to cover the next meter, and 1 second to cover the next meter, and so on. We say that the ball is traveling at a constant velocity, or that it is displacing equal amounts of distance, or we say that it has equal displacements in equal time intervals. So we can show that on a position time graph where we put time on the horizontal axis and position on the vertical axis. And we say that if the ball travels 1 meter in 1 second, we can plot that. In the next interval, it has traveled 2 meters in 2 seconds. And if we take another snapshot of it right here, we would see that it's traveled 3 meters in 3 seconds, and 4 meters in 4 seconds, 5 meters in 5 seconds, and 6 meters in 6 seconds. And you can see that we get a very nice straight line graph, which tells us that it is uniform motion. It's going at a constant rate. And maybe the measured distance isn't exactly falling on that line. Maybe we were slow with the stopwatch, or there's something wrong with our timing equipment, or our photography equipment isn't quite right. We still would draw a straight line, and we call this a best fit line. It's a smooth curve or straight line that most closely fits the general shape through all the plotted points. A best fit line is meant to mimic the trend of the data, and on paper we can get beautiful, perfect straight line graphs where all the points end up on the graph, but in reality we have something called experimental error, and we will get points that don't fall exactly on the straight line. That doesn't mean we just connect the dots, because that's not showing the trend. We know that the trend should be a straight line, especially in a position time graph. So we draw a best fit line to mimic that trend of data. When we talk about straight line data, we also end up talking about slope. Slope describes mathematically whether a line on a graph is horizontal, whether it goes up, or whether it goes down. There's three different kinds of slope. The first kind is positive slope. This is where the line slants up and on a position time graph. This indicates that an object's position from the origin is increasing with respect to time. A straight line means that the object is moving at a steady rate. In other words, the displacement for each time interval is uniform. An example would be a golf ball that travels to the right toward the hole. Notice that we said to the right, and that's why it actually comes out as positive. Zero slope on a position time graph is a horizontal. This is where the golf ball doesn't move for a period of time. Like, for example, when you missed your putt and it didn't make it all the way to the hole and you have to wait for your next turn to putt out. The graph would look like this. Time is passing, but the ball is not changing position. Negative slope is where the line slants down and to the right. For example, when the golf ball travels to the left past the hole. We'll get more practice with these. After the video, try the activities that follow on this page, analyzing a position time graph